day 17, lesson 11. Make sure you have that out, please. All right, today we're going to be looking at solution sets for equations and inequalities. Guys, we have a lot of things that we're going to accomplish, hopefully, in this lesson. Hopefully, you'll understand that an equation with variables is often viewed as a question asking for a set of values that one can assign to the variable of the equation to make the equation a true statement. All right, hopefully you're going to understand the commutative, associative, and distributive properties as identities. So this packet is a little long, but we're just going to kind of run through it and see what we can get accomplished. All right, so consider the equation x squared is equal to 3x plus 4, where x represents a real number. Are the expressions x squared and 3x plus 4 algebraically equivalent? In other words, are they the same on both sides? They are not. So they are not algebraically equivalent. So we cannot guarantee that there will be any real value of x that will make this equation true. So it says the following table shows how we might sift through various values to assign to a variable symbol x in the hunt for values that would make the equation true. So in other words, they're saying, let's just put some numbers in there and see what happens. And they said, well, if we let x equal 0, it's not true. If we let x equal 5, it's false. X equals 6, it's false. X equals negative 7, it's false. Let's let x equal 4. Oh, look, it's true. Let x equal 9, false. X equal 10, false. X equal negative 8, false. Of course, we would sift through all the real numbers, and guys, you realize that would take forever to go through every single number that we could if we were seeking the values to make the equations true. That would be a huge table. So far, we have found that setting x equal to 4 gives us a true statement. Look at the image in your packet. Okay? Can you see what's happening here and how it relates to what we've been discussing? All right? So, looking at this image, and I was making sure there wasn't anything on the back to deal with this, can you figure out what's happening here? Well, the numbers are going down, and you can look at this as a road if you would like. The numbers are going down the road, and they're being accepted into the solution set or being rejected. All right, so I can look at it here. I've got numbers. 4 has been accepted, so it went past the gate. 0 is over here because it was false. It was rejected. All right, and it says these are the ones that are rejected. These are our solutions, and 3 and 2 are still waiting to come. And when we put 3 in there, I don't know what's going to happen. We put 2 in there, I don't know what's going to happen. All right, so that's kind of a visual image as to what is happening here. Are they being accepted or are they being rejected as solutions to this? There happens to be just one more value that we can assign to x that makes x squared equal 3x plus 4 a true statement. We could continue that search to find it. All right? I'm going to tell you that if you let x equal negative 1, then we'll put that in there. So negative 1 squared is equal to 3 times negative 1 plus 4. All right, so I get negative 1 squared is 1. I'm going to put that question mark up here because I don't know if they're equal yet. 3 times negative 1 is negative 3 plus 4. 1 is equal to 1, so this would be a true value. Okay? I didn't want you to spend a whole long time trying to figure out what that other value was. All right. Example example number 2. Consider the equation 7 plus p is equal to 12. It says, fill out this table. Let p equal 4. So we're just going to plug that in. So 7 plus 4 equals 12. Is that true? No, that's false. Okay? All right, let's look at the next one. 7 plus 1 plus the square root of 2 is equal to 12. Well, 7 plus 1 would be 8, plus the square root of 2 is never going to be 12. So that's false. Let p equal 1 over pi. So 7 plus 1 over pi, is that equal to 12? No. Let p equal 5. 7 plus 5 is equal to 12. That is true. All right, so we've tried all these different things, and the only thing we found was p is equal to 5. But is a table necessary for this question? Is it obvious what value we could assign to p to make the equation true? In this case, this equation is pretty simple. I can look at it and say 7 plus what gives me 12? Well, 7 plus 5 gives me 12. So in this case, a table really wasn't exactly necessary. All right, so let's look at our box. The solution set of an equation written with only one variable is the set of all values one can assign to that variable to make the equation a true statement. Any one of those values is said to be a solution to the equation. All right, so solution set is everything I can put in there. Everything I can put in for that variable that will make it true. In this case, 5 is the only answer. Back here, my solution set would be 4 and negative 1 because I had 2 answers that would make it a true statement. So the solution set is everything I can put in for that variable. To solve an equation means to find the solution set for that equation. All right, so let's go on with example number 3. It says solve for a if a squared is equal to 25. All right, now here's the nice thing about this. Hopefully you know that a squared is equal to 25. I kind of have a perfect square here. All right. To solve this, I want to know what times itself would give me 25. Well, hopefully, automatically, it would pop in your head that a could be equal to 5. Because 5 times 5 gives me 25. But here's the nice thing about this. Or maybe it's not so nice to you, but here's the funny thing about algebra. Guys, we don't only deal with positive numbers, we deal with negative numbers also. So, is there any other solution for this equation? What if I let a equal negative 5? Negative 5 times negative 5 gives me positive 25. All right? Most of you would jump here and say that's it. A would be equal to 5. Most of you probably did not think about a being negative 5. But negative 5 would work. All right? So we're going to assume both of these values work. One can describe a solution set in any of the following ways. You can describe it in words. A squared is equal to 25 has the solution 5 and negative 5. Or you can say a squared is equal to 25 is true when a is equal to 5 or a is equal to negative 5. So you can write it out in words. All right? You can do what we call inset notation. The solution set of a squared is equal to 25 is negative 5, 5. Set notation is simply using these funky looking brackets and I'm not going to grade you on how well you can draw those brackets. And then I simply put my answers inside there. And normally we do them from least to greatest. So notice -5 and 5. All right, -5 comes first. So that is set notation. Or we can represent it graphically on a number line. So I can draw a number line and I can put a dot at -5 and I can put a dot at 5. So here are 3 ways, and star these because they're going to become part of your best friend. 3 ways that you can describe a solution set for an equation. In this graphical representation, a solid dot is used to indicate a point on the number line that is to be included in the solution set. Warning, the dot only physically draws let me start over. The dot one physically draws is larger than the point it represents. One hopes that it is clear from the context of the diagram which point each dot refers to. So I use a solid dot on my number line. How set notation works. The curly brackets indicate we are denoting a set. A set is essentially a collection of things. Letters, numbers, cars, people. In this case, the things are numbers. From this example, the numbers -5 and 5 are called elements of this set. All right, guys, some very important information, very important vocabulary here. No other elements belong in this particular set because no other numbers make the equation a squared is equal to 25. A squared is equal to 25 true. Nothing else makes this true. When elements are listed, they are listed in increasing order. In other words, start with the smallest and go to the biggest. Sometimes a set is empty. It has no elements, in which case the set looks like this, empty. We often denote this with the symbol right here. It looks like a 0 with a slash through it. We refer to this as an empty set or a null set. Guys, this one's important. Remember we talked about sometimes there's nothing I can put in there to make it true? That would be an empty set or a null set. Alright? Alright, so solve for A. If A squared is equal to -25, present the solution set in words, in set notation, and graphically. Alright, so let's look at this. Is there anything I can put in for A that I can multiply times itself to give me -25? Well, I can work with 25. That would be 5. But can I get -25? No. So in words, the solution set to this equation is an empty set. Okay? There's nothing I can put in there to give me -25. Alright? Let's look at set notation. Remember, what does it say we can do? We can draw it just like this. Alright, empty brackets. There's nothing there. Alright, and graphical representation, I can draw a number line. I'm not going to put anything on it because there's no number that I can put in there that would work. Alright? Exercise number 2. Depict the solution set of 7 plus p is equal to 12 in words, in set notation, and graphically. We've already answered this one. Now they just want us to do it in words. What did we say is the only thing I can put in for p? 5. So 7 plus p is equal to 12. Has the solution p is equal to 5. Okay? Set notation. to draw my graph, and I'm going to put a dot at 5. Okay? And that's all I have to do. Example number 4, solve x over x is equal to 1. For x over the set of positive real numbers, depict the solution set in words, in set notation, and graphically. Guys, looking at this, x over x. X over x. In other words, it's not going to matter what number I put in there. Can I put 0 in there? No. But I can put all positive real numbers, and it's not going to matter. It's going to be true. So in words. All right, the solution set is the set of all positive real numbers. Okay? All positive real numbers. All right, now, I want you to pay attention to this here. My set notation is going to be written just a little bit differently. All right? Because it's not just, guys, I can't list every single positive real number. I can't start at 1 and list 1.1, 1.000000000000001. I cannot physically list every single positive real number. Okay? So it's going to look like this. I've got to define that x is going to be a real positive number such that x is going to be greater than 0. So it can be 0.00000000001, and it's going to work as long as I tell it that x has to be greater than 0. All right? Now, what's it going to look like graphically? It's going to look just a little bit different, because once again, I cannot put every single positive real number on my graph. Do you realize what that would look like? It would be unreal. So, I'm going to start, and it says x has to be greater than 0, but 0 is not included. So I'm going to put an open circle at 0, because remember, open circle means it's not included. And then I'm going to shade everything from 0 up. And that tells me that my solution can be anything after 0. All right, anything after 0. All right. I know that's kind of crazy, but... All right, so let's talk about set notation for just a moment. If it is possible to list the elements in a set, then you can do so. Okay? You can list 5, -5, whatever. If it's not possible, then this is what it's going to look like. Okay? I'm going to tell you what my variable is, and in this case it was x. Then I'm going to tell you what type of number, and it's a real number. And then I'm going to tell you what are the specifications. In this case, x has to be greater than 0. Okay? This is read as such that, okay? So x is real such that x has to be greater than 0. Once again, solid dot means it is included. Open dot means not included. Okay? So solid dot means it's included. Open dot means it is not included. All right? All right, let's look at example number 3. Solve x divided by x is equal to 1 for x over the set of all non-zero real numbers. Describe the solution set in words, in set notation, and graphically. So, here's the difference between this one and example number 2. It says solve for all set of positive real numbers. Here it tells me set over a set of all non-zero real numbers. So now I can look at this and say, can I include all my negative numbers? Is negative 1 divided by negative 1 positive 1? It is. Negative 100 divided by negative 100 is 1. All right, so here's why it's going to be a little bit different. All right, so here's words. So I'm looking at a set of all non-zero. So the solution set is a set of all non-zero real numbers. In other words, I can put everything in there except 0. I can put all positive numbers, I can put all negative numbers, but I cannot put 0. Alright, so then let's talk about what our set notation is going to look like. Is it possible for me to list everything? No, it's not. So it's going to look that little differently. Alright, so my variable, x, what kind of number am I looking at? I'm looking at real numbers, so x has to be a real number such that, what do I know about x? It can be any positive or negative number. The only thing it cannot be is what? X cannot be 0. So therefore, now I know that I can let x equal anything I want except 0. All right, let's look at it graphically. Closed dot means it's included. Open dot means it's not included. Where does my open dot go? What is the only number that's not included? 0. But now I'm going to shade all these numbers this way. And I'm going to shade all these numbers this way because everything is included except 0. So my graph is going to look like that. All right, let's look at the next example. Solve for x if x, parentheses, 3 plus x is equal to 3x plus x squared. Alright, since it's not specified otherwise, we should again assume that we are considering solutions from a set of all real numbers. In other words, we're going to assume it can be a positive number or it can be a negative number because it does not say all non-zero numbers or all real positive numbers. In drawing a table to sift for possible solutions, you might come to suspect that every real value of x is a solution to this equation. All right? The distributive property becomes a big factor here. X times 3 is 3x. X times x is x squared. All right? So, what is that going to tell me? In other words, that's going to tell me that it does not matter what number I put in, this statement is going to be true. Even 0. I can put 0 in there, and it's going to be true. I can put any negative number in there. It's going to be true. I can put any positive number in there. It's going to be true. So if I were to graph this, I would just shade the whole entire number line. Okay, so It's awkward to express the set of all real numbers in a set notation. So here's what we actually do. We actually have a way that we write this. So let's look at this. Words, the solution set is all real numbers. In other words, it does not matter what I put in there, 0 included. Set notation. Here's my set notation. What we would do is we would draw a double, it's a double vertical bar with the capital letter R. And it actually is Blackboard script. So if you were to type this, you would go to Blackboard script and type the letter R. But this is what it looks like. And it's just a double vertical bar as a capital letter. Okay? So this tells me that all real numbers work. And then if I were to look at it on the graph, like I said, guys, I would just, it would be everything. Okay? It would be everything. All right, exercise 4. Solve for A. If A plus A squared is equal to A times A plus 1, describe carefully the reasoning that justifies your solution. Describe the solution set in words and set notation and graphically. Okay, so what do we notice? Look at this, guys. A plus A squared is equal to A plus 1, or A times A plus 1. Here's what I would do. Because I have parentheses, I would go ahead and look at distributive property just to see if by any chance it's the same. So A times A is A squared plus A times 1 is A. Look at this. Distributive property. Then I can use the commutative property, because remember, commutative property tells me it doesn't matter which way I add things. So by using the distributive property and the commutative property, we see that they're the same. So because they're the same, what does that mean? It's just like this one here. No matter what number I put in, it's going to be true. So make sure it didn't say, it just said solve for A. It didn't tell me positive numbers, negative numbers, or anything like that. So what's my solution set? It's all real numbers. So I've used the distributive property. All right. And then I use the commutative property. That just tells me I can switch things around. By using that, I see the solution set is all real numbers. So how would I write that in set notation? There's my capital R. And what would it look like graphically? I would be shading the whole entire number line. Okay? The whole entire number line. Alright, so really quickly, let's go back and think about this question. What does it mean to have two expressions be algebraically equivalent? One expression can be converted to the other by repeatedly applying the commutative, the associative, and distributive properties or properties of rational exponents to either expression. So when the left side of the equation is algebraically equivalent to the right side, our solution set is going to be all real numbers. An identity is an equation that is always true. All right? All right, now it's just a little bit longer. I know it's a long lesson, but there's a lot of information here. Trying to go through it as quickly as I can, but yet still get it so that you understand it. Identify the properties of arithmetic that justify why each of the following equations has a solution set of all real numbers. All right, so y, let's look at A. 2x squared plus 4x is equal to 2 times x squared plus 2x. What property can I use there that would show me that it's all real numbers? Well, remember what I said. When you've got parentheses, go ahead and use the distributive property and see what happens. 2 times x squared is 2x squared, and 2 times 2x is 4x. So distributive property tells me that these two equations are equivalent. All right, look at this next one. 2x squared plus 4x is equal to 4x plus 2x squared. What do we do here? They're the same on both sides. The only thing is the order's changed. And that would be our commutative property of addition. Because the commutative property of addition tells me that it does not matter what order I add my numbers in. 2 plus 3 is the same as 3 plus 2. All right, 2x squared plus 4x is equal to 2x times 2 plus x. Now let's look at this one. Go ahead and do that parentheses. So I get 4x plus 2x squared. It doesn't quite look the same, but I did use distributive property. All right? But I also have to do what? In order to flip them, I also have to use the commutative property of addition. Which would then change it to look like this. Because we remember we want them to look exactly the same on both sides of that equal sign. Okay? All right, create an expression from the right side of each equation such that the solution set for the equation will be all real numbers. There's more than one possibility for each expression. Feel free to write several. Guys, we're just going to run through and look at some of these. 2x minus 5, I could do what? I could flip them. Negative 5 plus 2x. They're the same on both sides. I've used the commutative property. X squared plus x. Guys, I could pull out an x and use the reverse distributive property and do x times x plus 1. 4 times x times y times z. Flip them around. You can rearrange these in any way you want. Z times 4 times y times x. It doesn't matter as long as I have the same 4 things on that side. And then x plus 2 quantity squared. I can rearrange everything inside the parentheses if I want. Or I can actually go ahead and factor that out if you want to do that. Like I said, there's some of these have different ways that you can do this. All right, so we can extend the notation of a solution set of an equation to that of a solution set of an inequality. That is a statement of inequality between two expressions. For instance, we can make sense of the following example. Solve for w if w plus 2 is greater than 4. All right, an inequality between two numerical expressions also has a well-defined truth value. It's going to be true or false. Just as for equations, one can sift through real values of the variable in an inequality to find those values that make the inequality a true statement. The solution set of an inequality is the set of all real values that make the inequality true. So let's look at this. Let's look at w plus 2 is greater than 4. Here's what you need to make sure you understand. Yes, I know that I can put 2 in there, but 2 plus 2 is 4. Is 4 greater than 4? No. So, I've got to think about this. Can I put 2.1 in there? Or 2.0003 in there? And it would be greater than 4. Yes, I can. So, W, if I were to look at this in words, W has to be greater than 2. If I put 2 in there, it wouldn't be right. But as long as it's greater than 2, I'm good. All right, so let's talk about what it would look like as set notation. All right, once again, it's going to be difficult to write everything because I'm looking at everything that's bigger than 2. So, my variable W, what kind of number is it? It's a real number such that, and then I have to tell it what's the special condition. W has to be greater than 2. And there's my set notation. Let's talk about what it would look like graphically. We said that it has to be greater than 2. Is 2 included? No, it is not. So open circle at 2, and then I would shade everything past that negative or that positive 2. Okay? I would shade everything past that 2. All right. Let's look at the last exercise. Solve for b if b squared is greater than or equal to 9. Describe the solution set using a number line. Okay, guys? We've got to use what we know. B squared is greater than or equal to. So it's got to be bigger or equal to 9. So it can be equal to 9. What would I put in there? Well, b could be greater than or equal to 3. Because 3 times 3 is 9. But what else could I put in there? Negative 3. So b would have to be less than or equal to negative 3. Why would it have to be less than negative 3? Well, if I put negative 1 in there, negative 1 times negative 1 is 1. Is 1 greater than or equal to 9? No, it is not. All right, so it says use it on a number line. All right, so here's my 0, 1, 2, 3, 4, negative 1, negative 2, negative 3. All right, so b is greater than or equal to 3. 3 is included because it's equal to. And then I'm going to shade everything that's greater than 3. b is less than or equal to negative 3. My dot goes to the negative 3. And I'm going to shade everything less than negative 3. All right. What is the solution set to the statement sticks of lengths 2 yards, 2 yards, and L yards make an isosceles triangle? Describe the solution set in words and on a number line. Well, what do I know about if it's a length? It has to be greater than what? Well, it has to be greater than 0. But in order for it to be a triangle, it would have to be less than what? Well, if I've got 2 length and a 2 length, it would have to be less than 4. All right, so L must be greater than 0, because I can't have a length of 0, but less than 4. Because when I'm drawing an isosceles triangle, my third side has to be smaller than the sum of the 2 sides. All right, so I'm going to draw my number line. Has to be greater than 0. 0 is not included. It has to be less than 4. 4 cannot be included. So it can be anything in between 0 and 4. Guys, like I said, I know this was a long lesson. I'm sorry, but there was a lot of material in there that I wanted to make sure you get. If you have any questions, reach out.